Okay, I hope that got your interest on the subject of negative temperature. Let's follow up on this topic. You know, if we pretend that temperature can be any value from positive to negative infinity, and here is a scale of temperature. It goes from 0 to positive infinity. Let's look at what happens, meanwhile, for the population value of n2 over n1. Okay, that is how many particles upstairs versus how many particles are downstairs. You know, as long as temperature is positive, then as I raise the temperature, you know, more particles will go up from downstairs to upstairs. Starting at when t equals 0, the population downstairs is 100%, population upstairs is 0. So this ratio of n2 over n1 at t equals 0 is 0. Okay, nothing is upstairs. As you increase the temperature, more particles are going to jump up, jump up, jump up, and this will continue until t reaches positive infinity, and that is when n2 equals n1, so the ratio stays at 100%. So you have a 50-50 split. Okay, now if we believe that the higher the temperature, the more particles go upstairs, then what happens when there are more particles upstairs than downstairs? Well, since n2 equals n1 at t equals infinity, if you want n2 to be greater than n1, then obviously the temperature has to be hotter than positive infinity, right? And how does that work mathematically? Well, mathematically, as we stated before, all you have to do is make t negative. Because delta E is positive. If t is negative, with this extra negative sign, the whole thing stays positive, which means you have e to the positive power, which is greater than 1, of course, then n2 is greater than 1. So you see, mathematically, it is possible to have more particles upstairs and downstairs. All you have to do is to make the temperature negative. As a matter of fact, let's take a look at what happens when temperature is negative. Okay, when temperature is negative but very, very, very large, say negative 1 billion degrees or whatever, extremely high temperature, then you know kT is much greater than delta E, right, in terms of absolute value. So you see this factor is very close to 0 on the shoulder of the exponential. So regardless of whether t is positive or negative, as long as t has a very large absolute value, this ratio is virtually equal to 1. So you can have negative infinity. The funny thing is, when t equals negative infinity, the effect is not that different from t equal to positive infinity, okay? Because after all, this exponential is almost equal to 0. Now, as t stays negative, but its absolute value decreases, okay? Then this ratio, the absolute value of this ratio will start to increase, which means n2 start to be getting greater and greater and greater compared with n1. As a matter of fact, when t is negative, but is very, very small, so that t is like what we call 0 minus. Okay, this peculiar sign means it is very close to 0, yet it is a negative value. Then you look at delta E over kT. Okay, delta E over kT is a very large negative value. You couple with this negative sign, you have e to the very, very large positive power, which means it's far greater than 1, which means nearly 100% of the particles will be upstairs, nothing will be downstairs, and that happens when t equals negative, but very, very small value. Okay, and this ratio goes to infinity. Again, if you believe that the greater this ratio n2 over n1, the higher the temperature, then guess what is really the hottest temperature of them all? Well, it is no longer positive infinity. It is a negative value. And how negative? Negative 0, which means it's negative but very, very, very close to 0. Now, isn't that weird? Physically, this region is physically allowed. Okay, but it turns out that when you see n2 greater than n1, you have to interpret this as a negative temperature. The question is there such a thing, such a system in nature such that n2 is greater than n1? Well, the answer, surprisingly, is yes. Not only do we have such systems, it is actually fairly common. You have it in possession. You have it in your house. You probably have it in your car. You probably even have it in your backpack. And certainly in your computer. Okay, you wonder what this is, right? Give up? Okay. You know, you want a system with more particles upstairs, less particles downstairs. Particles upstairs can actually go downstairs by giving up some energy. Okay, because the start was higher energy, end was lower energy. So as they jump downwards, they're going to give up the energy. That energy is emitted in terms of a beam of light, okay, which is called a photon. Of course, particles can also go from downstairs to upstairs. In doing so, they have to absorb some photon, okay, because they have to acquire energy. But since there are more particles upstairs than downstairs, the net effect of this system with population inversion is that more photons will be emitted and less photons will be absorbed. So this is a system which overall will emit photons. And when you have a large number of particles upstairs, then as they crash downwards, they're going to emit a lot of photons. What you get is a beam of very intense light whose frequency is precisely determined by the difference in energy levels. Okay, think about a beam of very intense, color-pure light. What do you think that might be in terms of modern technology? Yes, how about laser? What is laser? Laser stands for light amplification by stimulated emission of radiation. That's what laser stands for. So, to make laser work, we must achieve what's called population inversion. So more photons will be emitted, less photons will be absorbed. And mathematically, that would correspond to what's called a negative temperature. Okay, now, I've said that before, negative temperature is hotter than positive infinity. Doesn't that mean that the laser, the DVD player or CD player in your pocket is hotter than anything you can ever touch? Hotter than positive infinity? Isn't that going to melt everything away? That doesn't sound to make any sense, right? Okay, here's the thing. Negative temperature is not a real temperature. That's why I put it in the quotation mark. Okay, it is only mathematically equivalent. So that when I allow this temperature to be artificially negative, I can still use the same Boltzmann distribution law to describe the population inversion. That is the fact that N2 is greater than N1. This is not a real temperature. Why? Because how did we define temperature? How did we measure temperature? We put two substances together, right? Allow them in thermal contact, right? Eventually reach the same temperature, and we say, okay, when that temperature is reached, no further exchange of heat will occur between them, and they have achieved something in common, which is the same common temperature. And then we say, this is the temperature we can measure. The system is left alone, okay? It is not in thermal contact with the environment. You allow these two positive systems to exchange energy. That's all you do. Eventually reach the same temperature. Okay, how does a laser work though? You know, common sense tells us that in order to shoot a laser beam, you have to plug the laser into a power source, right? Such as, electrical power outlet. That means that it takes energy to pump those particles from downstairs to upstairs. You have to keep on pumping because the particles naturally don't want to go upstairs. You have to force them up. That's called optical pump, okay? You have to use an optical pump. Essentially what that means is that using electrical energy that is fed from outside energy source, and you use that energy to pump the electrons from downstairs to upstairs. Once they're upstairs, they have a natural tendency to want to jump down, and therefore they will emit photons. That's how a laser works. So you see, this is not a system that is self-sufficient. It is not a system that achieves this state by itself. You have to plug into a power supply. It has to exchange energy. In fact, it has to obtain energy from the outside world to maintain such an artificial state of population inversion. Okay, it is not left alone. It is not an isolated system. Therefore, the temperature here is an artificial indicator. It is not the real temperature, because the real temperature is when something reaches thermal equilibrium. You leave it alone. You don't have to give it any energy or anything. It reaches a final temperature, and that negative temperature, or population inversion, is artificially sustained by pumping energy into the system. So don't worry about your DVD or laser player melting everything, okay? This is not going to happen. But it's an interesting concept, negative temperature. All right, now let's look at a numerical example on what kind of relative population numbers we can expect. at a given temperature. Suppose we're looking at a real atom, okay, the hydrogen atom. Hydrogen atom has the lowest energy level, that is what's called ground state. The ground state is the lowest possible energy level. And then the energy level that's a little bit higher than that, okay, only higher than ground level. It's called a first excited state. And the one that's higher than that is called second excited state, and so on. Now, the energy difference between these two states can be calculated using modern physics, and it turns out to be 10.4 eV. Okay, what's eV? 1 eV is called electron volt. It is a unit of energy. It is much, much less than 1 joule. We learned the details in physics 1C because it has to do with how to accelerate an electron and so forth. But all we need to know now is that it's a very small fraction of 1 joule. It is a convenient unit when it comes to measuring the energy of atoms and molecules. It is equal to 1.60 times 10 to the negative 19 joules. Okay, it is a convenient unit for measuring atomic and molecular energy levels. Now, the temperature is at room temperature, 300 Kelvin. Okay, what I want to know is if you have a whole bunch of hydrogen atoms at 300 Kelvin, okay, in thermal equilibrium, they reach the same final temperature, 300 Kelvin. My question is, how many atoms will stay at the ground state? How many atoms will be at what's called the first excited state, which is 10.4 eV above the ground state? This is what I want to know. Well, that depends on this Boltzmann factor, right? This is state 2, this is state 1. We know that N2 over N1 equals e to the negative delta E over KT. Right? And this K is the Boltzmann constant, T is 300 Kelvin. Delta E is 10.4 eV. Okay, so what we need to do is to figure out this ratio delta E over KT. Delta E is measured in eV, and so let's measure KT also in eV as well. How do we do that? Well, KT, let's work it out. Okay, this is actually the Boltzmann constant, so it's 1.38 times 10 to the negative 23 joule per Kelvin. Okay, times T. T is 300 Kelvin. Okay, if you do so, you're going to get joules, right? Now we want to convert to eV now, so let's do that. 1.60 times 10 to the negative 19 joules makes 1 eV. Right? So that's the conversion factor. Okay, you cross out a K and cross out a J, you flip that eV over, you get eV. Okay, now if you did so, you can easily find the value of KT in terms of eV, and its value is actually pretty small. It is 2.6 times 10 to the negative 2 eV. This is, as a crude approximation, this is about 1 over 40 eV. Okay, that's a good thing to know, by the way. That is, KT at room temperature, 300 Kelvin, is roughly 1 over 40 of an eV. Okay, so you see, delta E is over 10 eV, right? And yet KT is a small fraction of an eV. It's only 1/40 of an eV, which means delta E over KT is a fairly large number. So you work out this number, you find this is e to the power negative 394. Okay, how much is e to the negative 394? I don't know exactly what it is, but I know it's very, very, very close to 0. This is far less than 1. What does that tell us? It tells us that at this temperature, the room temperature, almost all the hydrogen atoms will stay at the ground energy, at the ground level, so-called ground state. Very, very few of them will go upstairs. Okay, now as they go upstairs, they reach what's called the first excited state, and then they can jump back down. In doing so, they can emit a beam of light for us to see. Okay, so hydrogen can, just like any other atom, can emit light. when a higher energy atom jumps to a lower energy atom. But this is a very rare event as far as the number of hydrogen atoms are concerned, because almost all atoms will be in the ground state at the room temperature. Very few will be at the high energy state. Okay, because the ratio is e to the negative 394. Now, it doesn't mean you don't see any light coming from hydrogen, because even though this is a very, very small ratio, you're looking at 10 to the 23 to 26 such atoms all at once. So the absolute number of particles going here or even higher level is still substantial. It's just that the ratio is very, very small. Okay, now this also tells us when you look at a tank of hydrogen gas, okay, they bump into each other, right, through collision. In a typical collision, it's an elastic. Let's say it's a collision in which energy can be exchanged. What is the typical energy, kinetic energy carried by each hydrogen atom? We learned that 3½ kT, right? The average value, right? 3½ kT. So the order of magnitude would be kT, right? So at room temperature, each hydrogen molecule will have a typical energy of about 1/40th of an eV, the kinetic energy. As they bump to each other, part of the energy can exchange from one particle to another. Okay, but what that tells us is that in a typical collision, the energy that changes hands from one atom to another, or from one molecule to another, is typically only 1/40th of an eV. Is that enough for that particle to jump from downstairs to upstairs, crossing a gap of 10.4 eV? No. So that means that in a room temperature, usually when you look at molecular collision of hydrogen, or actually any other typical gas for that matter, the typical collision will not result in an electronic state transition from lower energy state to high energy state. Rather, it only makes the hydrogen atom go faster or slower. In other words, the overall kinetic energy, not the electronic energy inside the atom. That energy gap is too wide to be changed.